Share screen. Okay, awesome. So hopefully you guys can see that. And I'm gonna pin this video. All right. So we're just gonna go through these one by one. So again, this is how it's gonna be presented on the test. So you're gonna have just a whole mixture of these problems, and that's kind of the hardest part, is knowing which one's going through which pathway. So let's just start with number one. So number one, clearly we see that we have, I'm gonna abbreviate the benzene as PH, and we have kind of this CH3 and this bromine structure like that. And based on our reaction conditions, we see we have a pretty strong base, okay? And we have protic conditions, and we have kind of a secondary starting material. So this is all telling me an E2 pathway. So I'm thinking E2. All right, but we need to make sure in E2 that we have something known as the anti-coplanar configuration. Okay, so essentially let's just verify that by doing maybe a Newman projection. So if I'm looking down that bond axis, the Newman projection turns out to be something that looks like this. Okay, and with respect to the front carbon, which is, the leaving group over here, and the back carbon, which is the proton over here, they're anticoplanar. They're definitely in the right orientation. So in terms of drawing the right alkene, E versus Z, you can basically just do this shortcut where you see that, you have this methyl group and the phenyl on kind of this front side of this Newman projection, and the phenyl and the proton are on the back side. So that can really just translate to a structure that looks like this. Okay, notice the CH3 goes here, the pH is here, and that pH is in the back, and so is that proton in the back. So this tells me that this is going to be an E alkene. Okay, so that's kind of a way to get that E2 product. All right, let's go to number two. In number two, we have, a linear structure over here. We have this ester leaving group, and we're subjecting it to potassium hydroxide and heat. So if we're thinking reaction conditions, what do we think? Okay, if we're thinking reaction conditions for two, no, we're thinking E2 as well, right? We're thinking elimination, that's a strong base. So we need to, again, verify that we have the right, orientation. So if I draw a Newman projection, based on that bond, I see that I have ethyl going up. I have, CH3 to my right, a proton down here. On my back carbon, I have ethyl going down, the leaving group over there, and the proton there. So, on the front carbon, we need this proton. We need this proton to really be where the CH3 group is, okay? So this is not the right orientation, okay? So that tells me that I definitely need to do some sort of rotation. So even that fact just tells me we're already in transform over here. So the fact that I know that I have to rotate probably means that I'm gonna get some sort of cis alkene, or maybe Z, depending on, what the substituents are. So I'm just gonna rotate this to get the Newman projection I want, okay? So I'm basically gonna rotate everything so that CH3 is here, E2 is here, H is here. All right, and on the back carbon, I want the same configuration of my substituents. Okay, so something like that. So now the leaving group and the proton are in the right structure. And again, you can use that same shortcut where the two alpha groups are on this kind of side of the Newman projection, and then the methyl and the proton are on the other side. So, in terms of what that might look like, I'm thinking something like that, okay? And this is gonna be a Z alkene. So that's my E2 product. All right, let's keep moving. So on 3, it looks like we have, this big molecule. And we're subjecting it to this methanol reagent. So what pathway do we think this is going to go through, or pathways? Okay, I see a lot of SN1. What else? E1 too. Great, you guys got that. So SN1 and E1. All right, so essentially we're going to know that our main intermediate is going to be dependent on that rate determining step. So we're going to get, you know, this secondary carbocation that's adjacent to this tertiary benzylic position, okay? And essentially we can do a hydride shift because we go through that rearrangement and we get a tertiary benzylic carbocation, okay? So now from this position, we can do the SN1 pathway and the E1 pathway. So if I'm considering E1 conditions, I can get the Zaitsev product by removing that proton. You know, your methanol can act as the base, deprotonate that, and form that alkene. Okay, so SN1 and E1 happen in tandem. Okay, something like that. And then you can also get the SN1 or the substitution pathway where it attacks the carbocation. So under SN1 conditions, you can also get all right, so you get those three products. All right, so E1 pathway and SN1 pathway both happen, okay? And I just see this question's popping up. Why is methanol SN1? It's a weak nucleophile, weak base, and it is coupled with a secondary, I guess, secondary substitute starting material. So that's all telling me the SN1 pathway. All right, so 4, essentially we have this cyclic structure. Okay, and it looks like we have sodium tert butoxide. So essentially, what does that look like? That is that. So we know that that is one of our bulky bases. So all of this is telling me E2 pathway. So we have 2 positions. We have beta 1 and beta 2. But again, this is going to be E2, but regioselective for the Hoffman product because it's bulky. And we said that that had something to do with the steric argument. Okay, so we're not going to be able to access beta 1, even though we could form a more stable alkene, but we can access a proton from beta 2. And then tert butoxide, you know, deprotonates that, donates the electron density, you know, and facilitates the removal of the chlorine. So essentially, you're going to get the less substituted Hoffman product, and that's all we get. Okay, so that's 4. And then 5. Okay, so for 5, we have this structure. And we're subjecting it to LDA and THF conditions. Okay, again, that's one of our bulky bases. We know that's going to be E2, and that's going to be our Hoffman, you know, product, our steric argument, same thing. So we have quite a few beta positions. We have beta 1, beta 2, and beta 3. And this might be confusing, excuse me, for some of you guys, because you're like, wait, I don't really know which beta position to pick from. Well, you know that this is going to give you the Hoffman alkene. That's the definition of this E2 pathway. So it's Hoffman. So which beta position gives you the Hoffman alkene? Well, clearly it's beta 3. So essentially, you're going to remove a proton from here. That donates in and facilitates the removal. So you get that structure, this geminal alkene. Okay, so that's 5. All right, 6. Okay, so in 6 we have. Okay, so I think a lot of people are confused on this. Let me go back and answer that. So 5, again, why did we pick beta 3? So the definition of the E2 pathway with a bulky base is that it gives you the Hoffman alkene, okay? So just like we saw above, we got the Hoffman alkene. It was obvious in this case because we had a more substituted and a less substituted position. But in this case, they kind of like, even though this one kind of looks like it's close to this bromine and this crowdedness, like the proton does stick out, and it's the one that gives you the less substituted alkene. So that's kind of the expected product of this reaction. That's how I know to do that. Okay, so in 6. So 6 is going to be, I gotta scroll. Okay, so 6. So it's the same structure that we had before in 5. Okay. But essentially, we're going to do, what do we think? What pathway is that? Sodium ethoxide and ethanol. Yep, that's E2. And we need the proton next door. So we have beta 1 and beta 2. And we're looking for a proton that's on a dash. So if on beta 2, we already have a methyl dash, that only leaves beta 1 possible. Okay, so that's the right arrangement. And if you don't believe me, I'm going to just prove it to you with a chair conformer. Okay. Okay, so bromine is up on 1. So then 2, that means it's axial down. So that's the right configuration that we need for orbital, overlap. So that's, the situation that we have. And then let me just fill in 6. So 6, we're going to have methyl down an equatorial proton. So notice that the proton on beta 2, this is beta 2, is not accessible, okay, is not accessible, all right? So that leaves us, even though we have what the expected conditions would be to give a Zaitsev product, we're still going to get the Hofmann here, okay? So essentially, that end product here is going to look like that. And this, all right? So that's what 6 looks like. Right. So 7, and no, it's not racemic because notice on beta 2, we're not playing with the chirality there. No, we're leaving it. Okay, so 7 looks like we have the same exact material, okay? And we're treating it with water. So what pathway in the chat box do we think that this is gonna be? SN1, E1, great, SN1 and E1. So the main reactive intermediate is probably important to draw. So that's probably a tertiary carbocation. No rearrangements necessary. Water can attack that position. Okay, so we can get the 2 substitution products, so the 2 diastereomers. That would be this and that. Okay. So these are the 2 substitution products, SN1. Okay, and then we need the E1 pathway. So we're going to get the Zaitsev alkene. So that's the proton probably here. And that's going to give me this tetra-substituted alkene. And that's E1. All right, so you get those 3 products. All right, pretty easy. Moving on. So 8. Sorry, guys, I'm just trying to move fast because we have a lot of questions we need to cover today. So we have for 8, so it looks like something that would maybe want me to think ring expansion, okay? I see that I have almost that, adjacent carbocation, what seems to a 4 or 5 membered ring, but the reaction conditions tell me what reaction pathway. What do we think? SN2, right? SN2, awesome. So really, we don't have any carbocations forming, so no rearrangements, don't be fooled. But this is backside attack, remember, inversion of configuration. So we're gonna get, actually, a structure that looks like that. So this thioether, okay, and that's 8. Okay, so 9. So 9, we're gonna use that same, starting material that we just used. But now we're going to treat it with, CH3SH, so this thiomethanol, okay? So this is telling me what? What pathway? SN1E1, great. So I think I want you guys to notice that we can really have the same starting materials, but manipulate the reagent slightly, and we get, 2 completely different products or different reaction pathways. So the main intermediate here is actually going to be dependent on this, rate determining step. So we get, this secondary carbocation. We're going to do a ring expansion. Okay, so let's kind of refresh our memory there. So again, we said from the substituent, counterclockwise, number the ring. We know we're going to have now a 6-membered ring, and the members of said ring are going to be 2, 3, 4, 5, 6, 7. The new bond is between 7 and 2. Okay, and then also on 2, we had the methyl group. 3, we took electrons away from, so that's where the new carbocation is. 5 already had this methyl group, and that's, a good, rearrangement structure that we have. Okay, so then from there, the SN1, nucleophile can just attack, so we can get, the SN1 product, so I'll just write SN1, and essentially we get, I'm just gonna draw this, that, and this, and I'm gonna write that. And there would be 4 total stereoisomers, okay? So if you had to pick from a drop-down menu, you would have wedge, wedge, dash, dash, wedge, dash, and dash, wedge. So there are 4 total SN1 products. And then in terms of E1, we're gonna get the Zaitsev, product again. So we're gonna choose to select the tri-substituted over the di-substituted alkene, and that gives us, a product that looks like that, okay? And that's the answer for 9. So let's move on to 10. So on 10 we have, so now I try to mix in some chapter 10 material just so we can do a comprehensive review here. So we have this secondary alcohol, and then step 1 we're treating it with thionyl chloride and pyridine. Okay, so that tells me that's going to be an SN2 pathway. Remember, we proved that last class, that PBr3, so phosphorus tribromide, and thionyl chloride are both ways that we can convert these alcohols into, halo alkanes, specifically the bromoalkane and the chloroalkane, through SN2 pathways. So that's kind of the first thing there. And then in step 2, we see that we have, it looks like sodium azide and DMSO. So that looks like another SN2 pathway. So we have to watch our stereochem here. And essentially, for the product of step 1 is going to be a chloroalkane with the chlorine on a dash. Okay, that's the product of step 1. And then the product of step 2 is that azide, doing another inversion of configuration, making this product. Okay, so it was a way to get the azide. So let's say I started with this starting material, and I wanted to get the azide exclusively on, the same wedge configuration. I could do a 2-step SN2 reaction to get that same configuration. All right, so that's the product for 10. All right, so then in 11, we are going to have this, okay. And it looks like we're treating it with this base, okay, and this protic solvent and heat. What do we think? What pathway, guys? What do we think in the chat box? E2, great, I love it. This is E2. All right, so let's make sure, with our Newman projection that OTS is our leaving group. And, let's just maybe draw it from this perspective. So we have, on the front carbon, ethyl going up. We have phenol to the right, proton on the back, OTS, methyl, proton. Okay, so on the front carbon, yeah, it looks like we're pretty good with our rearrangement already. We have, we have our proton here, we have our leaving group there. This is not a bulky base, no. Our bulky bases are either LDA or butoxide or anything bigger than that, So this is actually just a strong base in this situation. So essentially, our stereochemistry is going to match. Remember, the phenyl and the methyl group are going to be on the same side. Okay, so maybe that looks something like that. And, the ethyl group and the proton are going to be on the back side. So the ethyl is going to be, okay, something like that. So this is my Z alkene. Okay. I kind of just flipped it over by accident. But yeah, this is the product. Okay. E2. All right, so let me scroll up. So, okay. So for 12, we have this, and that's a chlorine. And I guess it's the same conditions. Okay, so clearly this is going to be E2. I'm going to just kind of go right there. It's the same conditions as above, so it's E2. And we're going to get the Zaitsev alkene. So that's going to be, this. So we have this beta 1 and we have this beta 2. And, we can deprotonate from the beta 1 to give us this, di-substituted alkene, this tri-substituted alkene. So that's something that looks like that. Okay, so that's the product for 12. All right. I'm going to keep moving. So 13, we have this, benzoic bromide, and we're treating it with sodium cyanide and acetone. Okay, and what do we think? This is going to be what pathway? SN2, great, SN2. Okay, so it's just backside attack. We're lucky here we don't have any kind of stereochemistry to consider. So it's really just going to be CN. Okay, so notice that you did extend the carbon chain here. So you went from 1 to 1, 2 carbons. So an equivalent structure to this would be something that looks like, 1, oops, I think I drew this too big. 1, yep, that. So 1, 2, the nitrile. Okay, so just be aware of that. You add an extra carbon in these reactions. All right, so 14. So 14 looks a little funky. So we have this, we have that, this bromine, that methyl, and we're treating it to this. So reaction pathway in the chat box, what do we think? SN1E1, you guys got it? SN1 and E1. Okay, so the main intermediate is dependent on this rate determining step. So we're going to get this tertiary carbocation, this methyl, that dash. Okay, so then from the SN1 pathway, we can get just that, you know, 2 diastereomers of this. We could get the configuration that looks like, oops, I did a mistake. This, sorry guys, this should have been a dash. I didn't mean to do that. And then the other one we could have gotten was this one. Okay, so these are the 2 SN1 diastereomers we get. And then we can also get an E1 product. And it doesn't matter either beta 1 or beta 2 in this case, because we're going to get the same exact product. So in terms of the E1 pathway, it doesn't matter. You know, the product would look the same. So let's say I remove from beta 1, I'm going to get the alkene there. I get a dash there. If I were to move from beta 2, I get the alkene here and a wedge there. But if you pancake flip it, it's the exact same thing. So you get these kind of 3 products. All right, SN1 and E1. Okay, that's that. Okay, so then in 15, we're gonna have a pretty interesting problem. So if you guys are kind of dozing off, this is a good one to look into. So we have this kind of crazy structure and we're subjecting it to ethanol. Okay, so what's your reaction pathway? What do we think? Yep, come on, more people respond. Let's get some more participation. Let's see. What do you guys think? Yep, SN1E1, I like that. You guys are all on the same page. SN1E1, good. So the rate determining step is dependent on, you know, that bromine leaving. So we're gonna get a secondary carbocation, right? Ring expansion, awesome, you guys see that. So essentially, let's just do the same numbering that we're used to. Okay, so I'm gonna do that like this. So again, from the substituent inward, counterclockwise, 3, 4, 5, 6, okay? So we know that my next expanded structure is gonna be a 5-membered ring. So let's just draw that, okay? We know these are 4 and 5 attached to the ring, okay? The new bond is between 6 and 2, so then that must be 3. Okay, let's fill in the substituents. So on 3, we took electrons away. It looks like we took electrons away from 3, but there was also a methyl already on 3. And then on 2, there's a methyl, okay? So that's kind of our expanded structure. And then from there, we can have ethanol come in and attack in the SN1 pathway. So that would be something that looks like this. And obviously you get, you know, this is a chiral center, so you get the wedge version, the dash version, the wedge version, the dash version. So again, you have 4 total structures here, 4 stereoisomers. I only drew 2 of them, you know, with the exception of those. And then in terms of the E1 pathway, you are obviously going to get, so this one's complicated. I think, and Dr. Peterson would probably say like ignore elimination products for this one. But the reason why I'm saying that is there are 2 beta positions where you get 2 equivalent tetra-substituted alkenes. Like if I were to move from beta 1 versus, you know, beta 2, I get, you know, a mixture of alkenes. So I'm not sure if she would want you to provide both. She'd probably give you more clarification on the test. So you get, you know, this alkene technically, and you could also get, you know, that one as well. So I don't know what she'd probably give you more clarification. Maybe the one she would say the one that produces the smallest amount of stereoisomers, so this one, but you know, she'd probably give you more information there. All right, but essentially, you know, you would know how to go through this ring expansion and get the SN1 pathway at least. All right, so we're almost done. So on 16, we have, you know, another cyclic structure. We have this and that, and we're looking to, what conditions do we think this is? Sodium ethoxide, ethanol, heat, what do we think? E2, great. We're looking for a dashed proton, okay? Dashed proton, I like that. This is beta 1, that's beta 2. Moving from beta 1 is gonna give me the Zaitsev, and I want Zaitsev in this case, so more substituted. So pretty easy, and I'm just going to get, you know, this lovely structure, that tri-substitute alkene. All right, okay, we have 2 more left. So then 17, we have what looks like similar structure, a different stereoisomer, and same conditions. So I'm just going to say E2, and this is going to be Zaitsev, right? Zaitsev conditions. So that means that I want to remove a proton to give me the more substituted alkene. However, we don't have a proton that's in the right spot. So that means we actually are going to get the Hofmann product, although we're predicted to get the Zaitsev. So the only option is to remove the proton from this beta position to get this chiral alkene product. All right. So that's that. All right. And then let's move on to 18, last one on this worksheet. So we have this structure. Okay, we have, okay, and we want to propose two SN2 reaction pathways. Oops, let me fix this. Okay, so we want to propose two SN2 pathways. So I can see, what if I cut here, 1, and what if I cut here, and 2? So let's kind of, break that down. So if I cut here, that means that the right side of 1 is the alcohol. So that would be, maybe that, and DMSO, that's my main nucleophile. Okay, and then maybe my starting material was this bromide. So, okay, so you guys can see that those would be the first set of conditions. But now if I consider 2, let's say maybe this is my nucleophile. So it could be, and then this could be my bromide, or source of carbons, right? So you could just basically break it up into 2 sides. And those are my 2 SN2 pathways, all right? And that's it. So I hope you guys liked this worksheet. I tried to, make it decently difficult. So if you guys felt this was decent for you, then you guys should be really good for your test, okay? This is hard stuff. This is hard material. So don't be discouraged. You still have a few more days, and you're going to be able to watch this video over again, and you can, listen to every single one of my explanations again and again and again until you get it, okay? It seems like a lot of you guys are talking about 18 right now. So it's just, we're proposing 2 SN2 pathways to get this ether. So this is a very common, reaction called the Williamson ether synthesis reaction. You're going to do it in the Orgo lab. So I think Dr. Peterson or Dr. Habnick actually mentions it by this name. So I definitely know how to make these SN, and it happens through an SN2 pathway. Okay, so basically what you can do is you can take this ether, okay, any ether. So let me take a different example. Let me take, like I literally just made this up, right? And I want to say propose 2 SN2 pathways that can, provide this ether. So essentially, let's cut them 2 sides. So let's just do, that's the side 1, and let's call that side 2. So let's look at side 1. So from side 1, anything to the left of that line, so look to the left of this line, let's say that is going to be my haloalkane. So let's make that the bromide. So it's the exact same thing, but just a bromine. So that's what's going to be attacked by the nucleophile. And then now to the right, this is going to be my main nucleophile. Okay, so that's going to be, okay, so let me just put Na. Okay, and then DMSO maybe as my solvent. And that's going to be those reagents sufficient enough to perform an SN2 pathway to get there. But another way, let's consider part 2. So maybe everything to the right is my haloalkane. So maybe it's this. Okay, and then this is my main alcohol or my main nucleophile. So alkoxide. So, okay, so did you guys get that? So it's just basically switching O and Br essentially. Okay, and those are 2 different ways to get it. All right, so that's enough practice for there. I want to have enough time to go into our practice exam. Okay, so we're gonna go and to do that right now. So I'm gonna share a different screen. Actually, maybe it is already on here. Okay, so we're on practice exam 4B. Okay, so if you guys take a second, everyone take like a little water break, whatever you need, pull up 4B, and we're gonna go through all the things that we already talked about in our office hour sessions. Okay. Okay, so we're gonna start. So essentially, we're going to skip the nomenclature. I think that's kind of a waste of time. But we are going to just jump into these. And then I have some critical thinking questions to do after this practice exam that were at the end of the workbook. So I want to try and get through all of those. So essentially, this is really important. And I kind of showed this in the previous office hour session, is that we're going to need to be able to rationalize how the rate can change if I manipulate a reagent or the substitution of a starting material. So let's just kind of take, each reaction condition, A, B, C, D, E, and F. One at a time and see one or two, which one goes better. So in A, it clearly looks like we're having some sort of SN2 reaction. I see a strong nucleophile, a polar aprotic solvent, and I see a primary, substituted starting material. But now I guess it comes down to which leaving group is better. So the better leaving group is the weaker base, okay? Or we can rationalize it's the more stable structure. So out of a chloride anion leaving or the hydroxide anion leaving, which one is more stable? Yeah, number one. Number one is the correct answer because a chlorine leaving, a chloride leaving, it would just look like this versus hydroxide. This is just a complete octet, single atom. Whereas this is a charged species and it's electronegative and, there's some sort of significant polarity there. So this is definitely more stable. It's a weaker base than the hydroxide. So weaker bases are better leaving groups. All right, and then in B. So it looks like, again, we have another, actually two different things. We have what looks like, oh, okay, I see. So we have a primary starting material. So the starting material is the same. The reagent is the same. So it looks like maybe a strong nucleophile, it could be. But what's changing is acetone versus methanol. So I don't really know a reaction pathway possible with B1. Like we have a strong nucleophile, but polar protic conditions, and then a primary starting material. Like I don't like any of that. So honestly, that's not really ringing any bells with me. I would really think 2 is the best one. That reminds me of an SN2 pathway, and all the conditions are favorable for such. All right. So again, I would pick 2 for B. For C, so we have, I guess it looks like 2 free radical bromination reactions. And remember, the 2 intermediates, it's proton abstraction. So we abstract from the more substituted position. So if for 1, I'm removing this proton, okay, and that generates this main intermediate. We go through this radical intermediate. And then in 2, we had actually this methyl group. So what's actually happening is we were abstracting the proton from that position, we're getting a tertiary radical. So since we went through this tertiary radical intermediate, it's actually more stable because it's lesser in energy, and that's why reaction 2 in part C is the better one. Okay, good. Okay, so for D. It looks like we're probably going to have some sort of, this looks like SN1 to me, or SN1E1 to me. It just looks like we're going to have the rate determining step where that bromine leaves on its own. And then the, acid, that carbonyl of that acid can, so I'm talking, here, let me just kind of prove this to you guys. I'm assuming that we have this, and we have the, carbonyl of this acid. Remove that, and you can get an E1 product. So I think you get both of these probably. Probably get the E1, and then you also probably get the SN1. So I could have had, SN1 addition into there. But essentially, which one is better? Well, you're going through a carbocation intermediate. So is this one, or is it this one? Okay, going to be more stable. Well, with this intermediate or that intermediate, this one's more stable because it's secondary allylic. It resonates. So that's why D2 is the better one. Okay. So in E, sodium amide, that should remind you of, alkyne preparation, specifically the acetylide reaction. So we can just rationalize that that's a base, a really good base. And these are, either a tertiary or a secondary starting material. So we're thinking E2. And I really think that the, I see, if you look at number 1, you get a tetrasubstituted alkene. Where number 2, you would get a tri-substituted alkene for your side product. So since your product is more stable, you have a greater driving force for that reaction, and that's why E1 is the better one, because you form that tetra-substituted E2 product, not the tri-substituted E2 product, all right? And then in F, we're doing dehydration conditions. Remember, it goes through an E1 mechanistic pathway. E1, remember, dehydration of alcohols, E1. And we see that we have, in part 1, the main carbocation intermediate generated from that elimination step, that rate determining step, is really this secondary, secondary carbocation. And then part 2, it's going to be this secondary carbocation as well, but there is no rearrangement, so no rearrangements. Okay. So now here we actually have another rearrangement that's possible to get the secondary benzylic position, right? So the problem is the question here is asking for which one is the faster rate. Well, because this goes through an extra rearrangement step, it's actually slower. Do you guys see that? It's actually slower because even though it's going through a more stable intermediate, it takes longer to get there because you have a whole nother internal rearrangement step. So really that's why 2 is the faster example. That's interesting. That was kind of a trick question. All right. Anybody need another explanation for F? That one was a little tricky.
Hey, Stephen.
Yeah.
I think number 2 for F is tertiary. I think you dropped the methyl there.
Oh, I did. Thanks for catching that. Okay. Yeah. So this would be a tertiary. So again, another reason. So then you can go about it another way. This is tertiary and then that's secondary. So because this is more stable, it goes faster. We actually looked into the answer the same way, but that's the better logic, is that this is a tertiary carbocation, this is a secondary, this is more stable, so it goes faster. Thank you for catching that. Okay, so we're going to move on to this mechanism real quick. So hopefully you guys can see my paper. Okay. So here we go. So draw a stepwise mechanism for the reaction. So we have this starting material, this alkene, we have this hydroxide, and we have phosphorus tribromide. So this is one of the Lewis structures I said you should know. Okay, so essentially the hydroxide is going to act as a nucleophile that attacks the phosphorus, okay? And in that step, we break a bromine bond, okay? So we are going to get, this bulky leaving group now. Somebody have a question? Okay. And then free bromide. So essentially we're here. So again, in an SN2 fashion, we talked about how all of these go through an SN2 pathway. This bromide is going to attack the front face and facilitate the removal of the byproduct. So you exclusively get really this main stereoisomer, and your byproduct is HO-PBr2. Okay, so there you go, that's A. B, how many stereoisomers of the major product would you expect? Well, this was SN2, so we get exclusively one major stereoisomer, which is the inversion of configuration. So for part B, it's one stereoisomer. C, draw the stereoisomer of the major product that would form. Well, C is that product. All right, so there you go. So we're going to keep moving. Let me scroll down. Okay, this is a great question. Okay, so this came up, before, so obviously on an old exam, so it's definitely the level that you guys should know. So there is an enzyme, purine, whatever, PNPase, that does this thing, whatever. So let's just kind of go looking at this reaction scheme. So we see we have guanosine. Okay, so this is this is the this is the sugar part, this is the basic part, this is the phosphate group, and essentially what looks like is happening is from this main sugar, this is this ether, the sugar down here, it looks like the leaving group might be leaving, this guanine might be leaving, that's why it's by itself here, and then at that position it looks like you're gonna get this incoming phosphate at that position. Okay, so you guys can clearly see some sort of resemblance of some sort of nucleophilic substitution reaction. Based on the substitution pattern and this leaving group, you can probably rationalize what pathway, but let's kind of go through what A says. So the chiral center identified by an asterisk, whatever, was observed to have a 1-to-1 mixture of R and S. So now that's more information. So what does that tell me about the mechanistic pathway for this reaction? Yeah, awesome. SN1, it was racemic. I love that. You guys are putting all this together. If it's 50%, the wedge configuration and 50% the dash configuration, then the only way to get that was through racemization or a carbocation intermediate or the SN1 mechanistic pathway. So yeah, part A is definitely going to be SN1. Awesome. Okay. B, which molecule is the leaving group on this reaction? Well, we kind of just proved that. That was guanine. Guanine was the leaving group. Okay. C, which molecule is the nucleophile? Well, the phosphate is what's coming in and replacing, and it's called the nucleophilic substitution. So the phosphate is clearly the main nucleophile. Okay. D, for the molecule that underwent substitution, draw the mechanistic intermediate of the reaction. Well, we said we have one-to-one mixture, which probably means racemization happened. So we had a carbocation. That's probably the intermediate they're talking about. And if we look back to our original starting structure, it was probably dependent, the rate determining step, on guanine leaving by itself. So I'm going to reproduce this below. And I think that's the main intermediate. So it was probably just, and here maybe I can draw this on the screen. It was really dependent on that mechanistic step. Okay, that bond breaking. All right. See, so it looked like a hard problem, but not bad at all, in my opinion. I don't think so. Okay, so we're going to keep moving. How do we get rid of this? There we go. And now we have a whole bunch of great product. Okay, so this is good. This is going to probably make you guys feel good at the end of this with all of your reaction knowledge. Okay, so for A, we clearly have, free radical bromination conditions. We're looking for, the most stable position. It's regioselective. And we're going to do this. Remember, one of the conditions was proton abstraction. We're removing a proton somewhere. So even though we're quaternary up here, we don't have a proton that can be removed, but we do have a proton capable of being removed there. So the main intermediate is actually going to be, this tertiary radical. Remember, radicals are sp2 hybridized. So we can have, again, a racemization type of situation here where we get the bromine coming on a wedge, forcing that methyl on a dash, and the other, an enantiomer where the bromine is on a dash and that methyl is on a wedge. All right, so that's A. All right, and this is how fast you guys should be at this point. All right, so for B, we have what looks like allylic bromination conditions. So remember that the main radical, I guess maybe I should say that the main reagent is N-bromosuccinimide, definitely a Lewis structure worth knowing. Homolytic cleavage results in this like stabilized, N-succinimide radical right here, and you get this bromine radical right there, essentially. And you go through this allylic mechanism, and again, it's proton abstraction, right? So you have to remove a proton somewhere. So you're right to think, we have allylic position 1, we have allylic position 2, and you would be right to think, position 1, because if there was a proton there, you can maybe rearrange and get a better substitute product. But there isn't one. So the only option is to really remove the proton here. So the radical you're really going through is this primary allylic radical. And even if I were to rearrange this, which is something you're always supposed to check for, you get this resonance structure, a lesser substituted alkene, actually. So we actually don't want to rearrange here. There was no reason to do that. So essentially, you just want to add the bromine to that position that you already had. So it's really just that. That's my product for B. Okay, does that make sense? So you're right to think everything that you already think, normally think, but in this situation, that did not happen. All right, so C, we have, what looks like E2 conditions. We have this secondary starting material. We have LDA, a bulky base. So we are thinking the Hoffman product, right? Hoffman. So honestly, I don't even actually have to think about, stereochemistry with this isopropyl group, because that's, the Zaitsev alkene, and we're getting the Hoffman alkene. Remember, we have beta 1, beta 2, and removing from beta 1 gives me Zaitsev, so not that one. But removing from beta 2 gives me Hoffman. So it's really easy, actually. We're just going to remove the proton here. So I can kind of just draw that. So essentially, you get this major stereoisomer, that one product. Pretty nice. Yep, LDA is bulky. Yep. So D. Okay, so in part D, let me move this up. Okay, it looks like we have some sort of, secondary alcohol starting material. Okay, and we're treating it with SOCl2. So that tells me SN2 pathway. Okay, so then the product of step 1 is going to be something that looks like that. Okay, so the chlorine's on a dash. And then in step 2, it looks like you're treating it with sodium methoxide and methanol. Okay, so basically this is telling me, I think elimination, I think E2. Okay, you guys should think E2, that's a strong base. And polar protic conditions. So we would expect to get the, Zaitsev alkene, but we're not going to get the Zaitsev alkene here because, again, we're looking for a proton on a wedge. If this is on a dash, we need the proton to be on a wedge, and here it's on a dash, but here it's on a wedge. So this is the right orbital alignment so that we're actually going to get the Hoffman alkene here, and that looks like this. So you get that one product. Okay, very good question. This is a very, very good question. Can I do that one? All right. Okay, so that was D. Let me move on to my paper. Let's move on to E. So we have this kind of iodine, okay? And then we have this, okay, and you're like, if your head is going like, what the hell is this? This is basically just an alcohol. This is essentially saying, basically you can think of it as methanol, So if that helps you, this is really going to go through which pathway? In the chat box, what do you guys think? SN1E1, both. Okay, it's basically just another way of saying SN1E1. We just drew out the line needle. This is actually isopropyl alcohol. This is isopropyl. Anyway, so the main rate determining step is dependent on the iodine leaving. So your main mechanistic intermediate is going to be that secondary carbocation. From there, you can get you have two elimination positions you can remove from, beta 1 and beta 2. In the chat box, which one is better? And it's interesting. It's beta 2. And so the reason it's beta 2 is because you're going to get actually two pi bonds next to each other, and that's a resonance feature. It's a conjugated system. You don't necessarily know what conjugation is yet, but you do know that conjugation is present, and you know that the fact that resonance is possible. So beta 2 is definitely the best position to remove from, so that alcohol can just, deprotonate and form this conjugated cyclic structure. And then you could also get addition at that point. So you could also get, and wedge, and you also can get dash. Okay, so you get that as well. So those three products are possible from this. All right, so then in F, okay, we have, this structure, okay, kind of funky looking. And we're treating it with tolusyl chloride. And remember, this was, a combination of toluene and sulfonate. So we're going to basically get this aryl sulfonate forming, and it retains the same stereochemistry. So we didn't really know a lot about it. All we kind of talked about was the fact that it keeps the same stereochemistry, and it forms this substituent called OTS. And then in step 2, it looks like it's going to be E2 conditions with sodium hydroxide and water. So that's going to give me E2, and that's going to give me specifically the Zaitsev. We want Zaitsev. All right, so that basically means that I'm going to remove a proton to form the more substituted alkene. Okay, so that would be, this position, and so essentially you get this structure. So yeah, I just noticed that. Okay, so I kind of skipped too many steps. So if this is on a dash, that's telling you that this is on a wedge. So clearly this is already the E format. So I kind of knew that I had to rotate because this wasn't the right conformation. So then I just went to Z. I kind of skipped too many steps. I knew that was going to kind of confuse some of you. But yes, this is the right answer. You're right, it was on a wedge. You have to rotate. Right now it was E up here, and then down here it's Z. Okay, so I kind of skipped a few steps because we already went through that. G, it looks like we're going to do some sort of oxidation of alcohols. Okay, I like these. So we're going to treat this with PCC and DCM. That was the weak oxidant, remember? So that's going to stop us at that aldehyde or ketone. And remember, where you have a condition for oxidation in organic chemistry is the loss of a carbon-hydrogen bond while we gain a carbon-oxygen bond. Okay? So essentially, we can do oxidation here, but we can't do oxidation here because there are no protons present. Remember, orgo definition of oxidation. Okay? Loss of carbon-hydrogen, gain carbon-oxygen. Reduction would just be the opposite of these definitions. Okay, so nothing is possible at the tertiary alcohol, but we can oxidize that primary alcohol into an aldehyde. Okay, so that's the structure we get. If I were to treat this instead with maybe Jones's reagent, or maybe one of the chromates, we've seen those were equivalents, we would get the carboxylic derivative, carboxylic acid derivative. That's the full oxidation. Okay. All right. And is that it for products, or is there more? Oh no, there's a few more. Okay, so H, I'm just going to do up here. Okay, so H looks like this. Okay, so this is pure lithium metal. And remember, that was another way of generating the alkoxide nucleophile. And essentially, that was just basically doing this. And then that alkoxide nucleophile can attack in an SN2 fashion with this haloalkane. So that's going to give you something that looks like this. Oops, not Br, sorry. And then that. So that is your main structure there. You only get one of those. And the last question is dehydration. Okay, so we have that, and this is dehydration. Remember, dehydration of alcohols is going to go through an E1 mechanistic pathway. So this is going to get protonated with the acid. It's going to leave on its own. You get this main intermediate. It's already in the most stable position, so we don't need to rearrange. Actually, that's a lie. Right now we have a secondary benzylic, but we could, have this alkyl shift to get, this new rearrangement. Watch. So if I remove this alkyl group over, I get this tertiary carbocation, but now when I deprotonate, I can get this tetrasubstituted benzylic alkene. And because this alkene is so stable, that's the driving force. So even though you kind of went from secondary benzylic to just a plain tertiary, like you did decrease in carbocation stability, but the payoff of forming the more stable alkene is the thermodynamic driving force. All right. Okay, let's move on to 5 real quick. Okay, we're running out of time. So for 5, essentially, we have this, okay, and oops, that's A, and we want to convert it into having a Markovnikov addition of Br. So that's probably like the first reaction you've ever learned. I would say hydrobromic acid. Pretty easy. Just putting a Markovnikov addition of a bromine. Then from there, it looks like we're forming this less substituted, Hoffman alkene. So I can choose a couple different things. I'm going to just pick a bulky base and say maybe LDA. So that was E2, and remember that was Hoffman. This was Markovnikov. Okay. And then from there, it looks like we're adding an alcohol to the less substituted position. Okay, so that's something like that, and that's probably hydroboration conditions. So maybe that. Okay. And then from there, it looks like we're getting an aldehyde. So that's probably a weak oxidation since it's going to be a primary alcohol. So my guess is PCC and DCM. All right. And that was a mini synthesis for you. All right, cannot be, oh, I'm sorry, that's a carboxylic acid. Thank you. This should have been a strong one. This should have been Jones or sodium dichromate or potassium dichromate, any of those. Okay, sorry, strong. Okay, all right, and I like that. So we can move on to, some of these synthesis real quick. We have 4 minutes left. So for A, real quick, basically, I'm thinking, I don't know what the hell to do. Let me just add an anti-Markovnikov alcohol. That's just my first intuition, purely because I see that there's something on that less substituted position of the alkene. Okay, that's like just the first thing I'm trying. I'm just guessing here. Okay, so basically that gives me, you know, this, and we know it's going to be chiral at that position. Okay, but what I can do is probably induce an elimination. So maybe I can do, I don't know, maybe I want to make this a better leaving group. Maybe let's make that PBr3. And that means that I still get a racemic mixture of haloalkanes there, all right? And then now I want a racemic mixture of this, you know, looks like an SN1 product if it's a carbocation pathway. So then what I probably want to do is just treat it with CH3SH, and you're at your product, and it's that easy. Yeah, that works. Okay. Anybody have any issues with that? Because you knew that, so the answer says racemic, so that's how I knew that it was SN1. Yeah, I don't know. I like that one better. And there's a lot of different ways you can do these, remember? And then B, let's just try that last one. Okay, so we have a secondary alcohol on a wedge configuration, and somehow we need to get to the aldehyde, but it looks like we get a byproduct. It looks like we're losing CH2O. Okay, so that's interesting. I don't really remember a way to do that. Maybe we'll get there in a second. But a way to get to aldehydes was to remember do ozonolysis. So I probably want to dehydrate and get an alkene. Okay. That gives me that alkene. And then maybe I can do ozonolysis to get these two products. Let me see, did I skip a step? Actually, I don't know if I can do that. Okay. So yeah, so I clearly can't do it this way. And the reason that is because if you look at the byproduct, it shows it's only one carbon. So if I were to cleave here, it's a 2-carbon fragment. So that clearly can't work. So this can't work. So another method maybe I'll try is, let's just convert this into a better leaving group. If I don't know what to do, a good place to start is make that a good leaving group. So I'm just going to make this, you know, a good leaving group. And then I clearly don't have to play with an alkene. So maybe just let me just eliminate and do an E2 pathway. So that would be something like this. Okay. Oh, that looks good now, because now I can do ozone and DMS, and that cuts here, and that gives me that 1-carbon aldehyde, and it also gives you that formaldehyde byproduct. You're there. Right? Guys, I have to go because it's 1 o'clock, but we did a lot of questions. I think we covered all of the material. I hope you feel good. I'm going to post this on YouTube. Good luck on exam 4. And next week, we're going to do some sort of review for your final exam. I don't know what yet, but see you guys.